Good afternoon, everyone. This is Richard from the Peking University, and this is my pleasure to present this work on behalf of Jiaqing Zhong from the National University of Defense Technologies. Because due to the visa issue, she cannot come here, and I will, on behalf of her, for the presentation. And the title of the work is CausalTuner, Future-Aware Causal Guidance for the Compiler Auto-Tuning. Yes, we all know the compilers are the bridge between the human intent and the hardware execution. So it acts as the fundamental arbiters of the performance, portability, and the productivity. By applying optimizations like the instruction reordering, loop unrolling, and the constant folding, we can fully exploit the modern CPU pipelines, the cache, and the parallel capabilities to speed up the program. However, the modern compilers like LLVM offers hundreds of optimization paths. Relying on the standard optimization levels like O3 often fails to deliver peak and application-specific performance. Because these standard optimization are designed for a general purpose instead of for the specific workload. Therefore, this brings us the phrase ordering problem. We need to select the right paths as well as the right order to achieve the optimal performance. Considering this example, if we apply the constant propagation before the dead code elimination, we could create a clean and optimize result. But conversely, if we revise this order, we may fail to remove the intermediate code. However, solving this problem is notoriously difficult. Currently, there are two main approaches, the machine learning-based and the search-based. The machine learning-based approach uses predictive models to guide the search or directly generate the optimal configurations. And the search-based program will search the configuration space to generate optimal path sequences. While the machine learning-based approach struggles to generalize across different programs, the search-based can easily adapt to any target program. So in this research, we focus on the search-based program. Though the search-based method could easily adapt to any program, but they still suffer from three key problems: the combinational explosion, the spurious correlations, and the search blindness. First, the combinational explosion means that the LLVM path permutations are very, very large. With over 100 LLVM paths and the sequences, there can be many paths long. The number of the possibilities grows like p to the L times L factorial. That is exponential as a factorial growth combined. To make the things worse, the evaluating just one candidate means a completely binary run, which is painfully slow. So with a limited resource budget, an exhaustive search is completely unacceptable. Second, the spurious correlations means that in the iterative search, some approaches use the models like the random forest or the Bayesian methods to narrow down the search space. However, they only identify the paths that are correlated with the performance without understanding the underlying mechanics. This often leads to the model to mistake the statistic noise for a genuine and causal improvement. So we can find that the correlation is not equal to the causation, and just relying on the correlation will be misleading. Therefore, we must address this to ensure a more robust and explainable tuning result. And finally, the traditional algorithm suffers from the search blindness because they treat the compiler as a completely black box. First, they cannot reuse the historical knowledge. forcing them to rebuild all configurations from the scratch for every new coming programs. And they are unaware to decode features, wasting the identical search budgets regardless of whether a program is loop bounded or control flow heavy. This brute force exploration incurs prohibitive overhead while completely missing out the structural clues that could prune the search space. Therefore, to address these limitations, we propose a CausalTuner framework as illustrated in this figure. It executes across three unique stages: the clustering, the synergy clustering, the causal mining, and the rule-injected online search to achieve a future-aware compiler auto-tuning with high sample efficiency. The stage one in this framework is the synergy clustering, which aims to alleviate the combinational explosion by clustering the programs based on the local pairwise path dependencies. And the stage two is the causal mining. It utilizes fast causal inference to screen out the spurious correlations and discover the robust causal rule size. And the stage three is a two-phrase rule-injected online search. It reduces the search blindness by leveraging the active causal mappings to guide the online search and eliminate the unpromising optimization branches. So let's look details to the framework. The stage one reduces the search space through key steps. First, the synergy matrix construction profiles the path sequences pairs to capture the order-sensitive interactions. It identifies the combinational benefits whenever TA plus TB is larger than TA and B. And then the subsequent extraction uses a greedy path search on the aggregated cluster matrix to extract and keep the top K unique maximal sequences. And finally, the cluster predictor utilizes a GNN-based embedding as well as a hierarchical clustering to group the similar programs for the targeted optimizations. The stage two focuses on the mining causal rules. We utilize the fast causal inference to recover the structural relationship by testing the conditional independencies. It is highly robust against the hidden confounders. Looking at the workflow in the left figure, the input data goes through the independence tests to generate a directed PAG. This process leads directly to the causal purification example shown in the right. The FCAI could effectively identify and cut off the spurious correlations introduced by the program feature F, as well as the corresponding statistic noise. And by eliminating these misleading passes, we could successfully capture the true intervention gains theta, allowing us to discover a robust causal rules for the future compiler tuning. And the stage three introduced the two-phase rule-injected online search. It contains two phases. The phase one is causal subspace sampling. It bypassed the traditional co-star problem by prioritizing the search within low-dimensional causal manifolds. It maps the static features directly to the causal size and extracts the highly optimized state pipelines within the first 50 iterations. And the phase two is the residual evolutionary fine-tuning. It employs the stratified mutation rates to protect the verified causal gains while aggressively exploring the residual space. Specifically, we found that the conservative mutation rate of 1% to 5% will lock in the core causal structure, but an aggressive mutation rate of 15% will shuffle the unverified options to escape the local optima. We evaluated our framework on an AMD platform using the LLVM clone with the standard O3 optimization as our baselines. For the future data collection, we extract the program characteristics directly from the unoptimized LLVM bit code that are compiled at O0. By leveraging the LLVM's instant count and print loop sparses, you could generate standardized statistics via the states JSON option. And our evaluation crossed a comprehensive benchmark suite, including the C-bench, Polygon bench, spec CPU, and we also include the Llama bench from the Llama C++ ecosystem to ensure a thorough validation across diverse workloads. And our evaluation focuses on 4 research questions. First, we want to know how does the CausalTuner compare with other auto-tuning approaches in terms of the overall performance. And second, we would like to know how do individual components of the CausalTuner contribute to its overall performance. And the third, regarding the generalization, we want to know can the learned causal rules generalize to the unseen workloads beyond the training side. And finally, for the interpretability, we want to know why is the causal guidance mechanism in the CausalTuner effective? And in other words, can we interpret what the CausalTuner learns? Addressing the first question, we analyze the overall performance and the convergence velocity. Across the 30 diverse workloads spanning the classic benchmarks and the modern LLM engines, the CausalTuner delivers a dominant 17.77% average performance leap. It comfortably surpassed the other approaches such as group tuner from the last year LCTES, as well as other methods such as Bayesian-driven BOCA. Crucially, by turning the exploration via the offline injected causal rules, the CausalTuner achieves a 14.30% speed up within the first 50 iterations. This shows that the CausalTuner could successfully conquer the notorious cold start problem of stochastic searches. And we also isolate the individual components of the core components in the CausalTuner. The ablation study reveals that the synergy clustering in the stage 1 and the causal mining in the stage 2 fulfill the orthogonal yet deeply complementary rules. Eliminating the synergy clustering will restrict the long-term scalability. It will cause the search to stagnate due to the spatial dimensionality. Conversely, removing the causal guidance deprives the engine of its early acceleration. And we can find that the true optimization accelerance is unlocked when both operate in the tandem. And to answer the third question, we test the zero-shot transferring capability of our rules onto the completely unseen and out-of-domain benchmarks. The CausalTuner shows the remarkable robustness when deployed directly onto the dense and complex spec workloads. And we further introduced the Llama bench, the native benchmark extracted directly from the Llama C++ framework for real-world validation. And we found that the CausalTuner treasures an instantaneous 23.21% improvement in the token generation throughput. So this confirms that the causal rules could successfully grasp the universal compiler architecture principles. And we also further perform a cross-hardware validation to test the architectural robustness. And to eliminate the hardware-specific bias or other environmental artifacts, we directly deployed the causal rules meant from our original AMD platforms to another secondary Intel platforms with the fundamentally distinct microarchitecture. And the cross-platform results indicate that the CausalTuner consistently outperforms the best baselines. This result demonstrates that it could capture the universal compiler architecture interactions rather than a platform-specific noise. Finally, we also evaluate the structural interpretability of our guidance mechanism. This differentiates the CausalTuner from other black box alternatives. A case study tracks the divergent program feature distributions, and the result demonstrates this transparency. For example, for some arithmetic heavy code, the engine could automatically prioritizing the algebraic reductions. Whereas the, the control flow interface, once the PHI node density across the 0.0037 threshold, it instantly injects the passes like memory to register to optimize the register promotion. Therefore, we can find that the CausalTuner establishes an auditable and red box optimization logic. Okay, let me conclude. The CausalTuner transformed the compiler auto-tuning problem from a completely blind and a heuristic-driven process into a transparent white box and causal-guided one. While we currently rely on some offline data for training, the future work could focus on online causal graph updates and also expanding to even more diverse benchmarks. So this is end of my presentation, and thank you for your time. Since I'm not know about the details of this work, I will try my best to take your question. And if you will find more detailed some questions, you can directly email the first author Jiaqing, and I list his email, her email in the in this. Okay, and thank you.
Questions from the audience?
Hi, thanks for the talk. So you mentioned that you try to identify features in the input program for clustering the program. And,
yes.
So do you do that offline ahead of time, or is it a part of the compilation?
Yes, this process is done offline. This is done during the stage 1, and we use several programs from the Cbench and extract their features to get some candidate subsequences.
Sorry, one more follow-up question is, you also mentioned that do you use historical data from compilations for selecting the pass sequences?
Yes, we use the historic information is from the also from the stage 1. We profile some compile sequences from programs in the Cbench, and we use this information to generate some rules with stage 2, and use these features to plus the input program, and use this information in the stage 3 to generate the final compiling option sequences.
Thank you.
Thank you.
Due to time constraint, we have to move on to the next talk. Let's thank the speaker again.